He's here now, doctor.
Yep. Now student is here. Mr. Joy Devanji, can you hear me?
Hello, sir. Yes, yes. Hello, sir. Hello, sir.
Yeah. Okay. So, so now the presentation time. So you are required to, I think, deliver 22 to 30 minutes PowerPoint slide presentation and covering the whole aspect of the thesis, but in a very concise form, right?
Okay. Okay, sir.
Yeah,
Okay, sir.
for your information, we have a internal, external examiner, internal examiners. We have dean representative and your beloved supervisor. And I think co-supervisor will be coming late. All right. And I
All
am
right.
here chairing the session and Dr. Jakir here. Okay. So without
Okay.
further delay, I would like to welcome you, Mr. Joy Dawanji, to deliver your presentation, please.
Thank you. Thank you so much, sir.
Yeah.
Sir, is it visible
No, I think that is a. Can you share again?
now?
I think it not sharing. I think.
Okay.
Can you share again?
Sure, sure, sir.
Maybe you can share your entire screen.
Yeah.
Now it's showing, right, sir?
You go to the presentation mode. Yeah. There. Presentation mode. Yes. Yeah. Now, okay. Go ahead.
Okay. Thank you, Chair. Good morning, good evening. Sorry, good afternoon. I'm Joy Devanji. I'm a master's student. Today I'm going to discuss with my research work what I have done in last 2 years in my master journey. And the research work is entitled with Design of V-shape Cantilever Beam-based Piezoelectric Microenergy Harvester for Biomedical Applications. And this research work is supervised by Prof. Dr. M.D. Shabiul Islam and co-supervised by Prof. Dr. Ong Ing Yong. So today I'm going to discuss with this content, introduction, literature review, problem statement, objectives, and proposed block diagram, research methodology, simulation results, reference, and what I have done in my 2 years in publication. So moving to the introductions, that first, energy harvester. Energy harvester is also known as energy scavenging from the conversion of ambient energy sources, example as solar, vibration, thermal, and fluid flow, which which can generate electricity for powering autonomous electronic devices or circuits. And piezoelectric materials have the ability to convert mechanical energy to electrical energy. The different types of piezoelectric materials have, but we are considering as a PZT-5H is one of the most known piezoelectric materials models. Mechanical vibrations. There is a lots of mechanical vibration sources. Example as vehicle is one of the most famous one. But here we are considering human body movement vibration because we are working our application is pacemaker device. That's why we are considering human body movement vibration. So that human body movements we are considering three types. One is walking, other one is running, other one is motion. And the frequency limit is 0 to 15 hertz for the human body can generate. Cantilever beam is one of the mechanical beam where who has one fixed end and another one is a free end, and it is help to uh, uh, generate frequency. And there is this is the requirements device, all of the electronic device features, and there is a 10 nanowatt to 10 watt, So, but for our applications, we are going to use 1 microwatt to 10 microwatt. There's a lots of applications, like example as home automations, the body area network, biomedical applications, predictive maintenance, autonomous WSN system, precision agriculture, temperature and freshness sensor, smart structure monitoring, tire pressure monitoring. In our case, we are considering biomedical application, example as modern pacemaker. And for the for the modern pacemaker device, I already mentioned that our frequency range, we are dividing this range into three parts. As one is human walking, which can be generated on 0 to 5 hertz, and running 5 to 10 hertz, and human motion then we 10 to 15 hertz. This is the sustainable energy harvester where we are using human vibration, and we are using as a piezoelectric material and piezoelectric energy harvester, and also we are using electrical inductor circuit where this circuit is basically used to enhance the voltage and also to convert the AC voltage to DC voltage. I will describe in later, and directly going to the pacemaker application. So moving to the literature survey, in our previous researcher work, we have been studied the lots of cantilever, different types of cantilever beam shapes, and the cantilever beam shapes also known as also considered as three different parameters: length, height, and thickness. Basically, our main goal is to find of the resonance frequency and power. So for the resonance frequency, the cantilever beam length, width, and thickness are the main parameters where I can generate the highest resonance frequency for the biomedical applications or the other applications. So there is a previous user was they are using that GT shapes, T shapes, arrow shapes, arc shape, preferred tapered shapes, rectangular shapes, E shapes, spiral shapes, T shapes, and V shapes also working. And for the V shapes, the I have considering two papers I have found, but one for the biomedical SIM methods and another one is used for automotive force unit. So in the first one, they are found the resonance frequency of 253 hertz, and another one is that they didn't mention that how many frequencies they found and how many power they found. For I also studied on the pacemaker device how many power they required, for the powers, they used also they are working also different types of shapes: spiral shapes, L shapes, and fan folded, and spring shapes. So for that shape, here we have found also the resonance frequency, and the lowest resonance frequency was the 10 hertz, and also the highest one is the 79.5 hertz for the pacemaker devices. So for the problems, like in our case, the battery is actually for the low powered electronic device, the inside the battery, like medical devices, example as BP machines and smart health watch, pacemaker devices, and also the most of the sensors are operated on batteries. It's really difficult to replace and also the recharge the battery, and batteries also create a biohazard. So for the all of the problems we have been examined, and also that we already got the literature survey from the all of the different types of shapes. We are considering V shape because V shape has the best ability to create to generate resonance frequency, and also it has the angle difference where it can be used easily in a human structure, sorry, in human body, and also it also generates the voltage. So in our research objectives, we have three objectives. The first objective is that we to design a suitable PZT-based V-shape cantilever beam at required resonance frequency for generating AC voltage, which can be generated in millivolts from mechanical vibration using finite element analysis method in COMSOL software. The second objective is to design an ultra low power circuit, energy harvester circuit for converting into DC voltage from AC voltage using LTSPICE software. My third objective is to implement and validate of the developed V-shaped cantilever beam with the design ultra low power energy harvester circuit into hardware to generate comparatively higher power in microwatts for biomedical applications as well as modern pacemaker. So in our proposed block diagram, we are the research work we are considering this work is a two part. One is mechanical part and another one is electrical part. So in mechanical part, first we have considering the input vibration as our human movement body, which can be considered found from the 0 to 15 hertz. After that, we have designed V-shape cantilever beam, and also we give the input vibration to that beam, and it will generate resonance frequency. After that, we are applying the PZT materials, and that resonance frequency converted into AC voltage. So basically, our device, our applications is working on DC voltage. That's why we have to convert this AC voltage to DC voltage. And another thing is that these voltage are generated are low because the frequency we have been generated it was low. So that's why for the low voltage we have been considered to enhance our voltage using the boost-up converter circuit. Before that, we are converting the AC voltage to DC voltage using AC-DC rectifier circuit. So after that, basically the human vibration is not occurs any time. So that's why we have to use voltage regulated circuit to maintain the voltage ratio. So after that, the voltage will also we are using here supercapacitor because as a supercapacitor has a supercapacitor is also operated as a battery because its discharge time is too long compared to normal capacitor. After that, it will go to the biomedical application. So in our methodology, at first we started with the investigation with the different cantilever beam shapes, and we are considering the V-shape cantilever beam. So after that, based on the literature survey of the parameters, we have considered some parameters and also designed the V-shape cantilever beam using finite element analysis method in COMSOL software. After that, we have investigated two things that if the resonance frequencies comes like in our range like 0 to 15 hertz, then we will go to the next step. If not, then we will go to the first step again. So if it is yes, then we have designed the ultra low power circuit in LTSPICE software. So if the booster voltage and also the AC/DC rectifier circuit, everything is fine, then we measure the output DC voltage. If not, then again we have to check the design again. So if it is yes, then we can go to the next step to integrate with the both V-shape cantilever beam and also the our ultra low power circuit for generate micro power. After that, we are going to use this power in biomedical applications. So in mechanical part in the results section, first we have been uh, we have designed this beam in finite element analysis method, which is used for the mechanical design who has the meshing meshing process, also the nodes process, and also the calculations are performed. So at first we are considering as one rectangular cross section beam, and after that we also consider the another rectangular cross section. Then we just apply the mechanical vibration in during the resonance frequency. We have been considered frequency and also the calculation of voltage. We have been used two equations. That one is that uh, f of w of fx equals to p divided by 2 pi l square, and also the root over 70 e divided by rho into g, where l is the length, w is the width, and t is the thickness, and e is the effective density. And another one is the voltage equation from the cantilever beam, and the voltage equation is this, and where a PV is also the known as the thickness of the beam, PP is the thickness of the PZT material, momentum, geometric factor, Young module of the beam, and EP is the Young module of the PZT material. These are the properties for the materials. Here we are using aluminum materials. Basically, it is used in human body. That's why we have to check the materials also, so that it can be harmful for the body. And that the parameters we are considering is the length 85 millimeter to 110 millimeter based on the literature survey, and width is the 5 millimeter to 2 millimeter 20 millimeter, and thickness is 0.1 millimeter to 0.36 millimeter, and acceleration and effective density and the module values are considered. So finally, these are the beams. These are the beams where this one is the length and this one is the width and this is the thickness. And so we found that the optimum resonance frequency is 14.374 hertz, which is our optimum resonance frequency for the application. For this frequency, we have found the voltage, and these are the voltage graph here. The 269 millivolt are the optimum voltage we have found here. Some additional results to the for the length, width, and thickness to calculate the effect of the resonance frequency. So this is the some pictures for the resonance frequency in the length effect. So these are the beams are we have been designed to take the parameters 85 millimeter to 105 millimeter. And finally, we have the results that to show the how length effect it will. So from the length effect, so here the frequency in y-axis we are considering the frequency, in x-axis we are considering the length. So here we can see that if the length is increased, then the frequency is also increased. And this is the width effect. So again, there we can see that if the width is increased, then also the frequency is also increased. And in the thickness also the same value. If the thickness is also increased, the frequency is also increased. These are the some another results for the voltages with different voltages. We have been considering this resonance frequency into three modes. In which first I mentioned in my introduction section that we're considering the frequency in three different ways, that is working, running, and motion. So for working, it is the range is 0 to 5 hertz. So for the 0 to 5 hertz range, we have been found the optimum resonance frequency is 4.4859 hertz, and on that frequency we found that voltage 47.56 voltage. This is the optimum voltage for the 0 to 5 hertz range, which can be considered for the working range. And this is the graph for the 0 to 5 hertz. And other one is that for the running range, considers the 6 to 10 hertz. Here we have found the optimum frequency is 9.87 and the voltage is 163. And these are the simulation results for the frequency, and these are the graphs for the voltage. And for again the motion, for the motion range, it will we consider the range that 11 to 18 hertz, where the optimum frequency will be can be found. So in here we have found that 14.374 hertz into, and also the voltage also we have found the 269 millivolt. So basically, this one is the we can consider we have to generate also the voltage. So that's why the highest voltage in the 0 to 15 range, and we have found this one. And this was the graph for 269 millivolts. So yeah, this is my second part that I mentioned in my proposed block diagram, that electrical part. So basically, in electrical part, first we have some sub blocks and voltage developer circuit, boost up converter circuit, voltage regulator circuit, supercapacitor, and load. So first we design and simulation that all of the circuits in LTSPICE. After that, we are going through the hardware implementation in breadboard on also the stripboard also. So this one is for my voltage doubler circuit. Here we are using voltage doubler circuit instead of voltage doubler circuit instead of the bridge rectifier circuit, because in bridge rectifier circuit it has some voltage drop. But if we use voltage doubler circuit, we don't have any voltage drop. So these are the input for the voltage doubler circuit. This input is found from the mechanical part. Basically, we have limitations of budget. That's why we are not we are not going for the fabricated that V-shape cantilever beam, and that's why for the equivalent that voltage we are using here the function generator to give the input. So this input is comes from the mechanical part, 269 millivolt and 14.37 hertz. And finally, we found here the 269 millivolt DC voltage in the as an output. These are the graphs for the voltage doubler circuit. And this one is a boost-up converter circuit. Basically, this circuit is used to enhance the output voltage, enhance the input voltage. This one is the 260 0.269 volt. It's really very low. So that's why we are using here this circuit, and this circuit is already give the output to 2.4 volts in simulation. And these are the graphs for the boost-up converter circuit. Finally, I mentioned that we have to use the voltage regulator circuit also. So here we are using the voltage regulator circuit, and the input is comes from the boost-up converter circuit is 2.4 volt, and finally we maintain the voltage regulator is 2.2 volt. These are the graphs for the voltage regulator circuit. And this one, the full integrated circuit, here all of the things here, that AC to DC voltage doubler circuit and booster converter circuit and voltage regulator circuit, and also the pacemaker load. So again, we have a budget issues. That's why we are not going for the directly go for the by the pacemaker. So for that we are using here the equivalent load for the pacemaker devices. And finally, we have been found the output voltage is 1.9 volt for the whole circuit and all of the drops. So, so after that, we are going after the examination in software. Then we are directly going to the hardware. So in hardware, these are my hardware setup. Here, the function generators. I already mentioned that the function generators is used to the equivalent load for the for the output of the mechanical part from V-shape cantilever beam. And these are my circuits, and this is the output where I will measure. So at first, the AC/DC voltage doubler circuits. So these are the AC/DC voltage doubler circuits. We have found the 274.2 millivolt. 274 millivolt is the voltage doubler. Sorry, voltage doubler circuit output DC. So basically, it's a very good thing from that we have been found in simulations, and also the same similar voltage. And from the booster converter circuits, the voltage also enhanced with the 1.9 volt and 1.9 volt. Another thing is that the booster um, uh, regulator circuit, voltage regulator circuit, we have also maintained the 1.9 volt, no loss here to compare with the voltage regulator circuit. Sorry, booster converter circuit. Finally, this is my full circuit. Uh, Finally, this is my full circuit, and we have been found here the 1.6 volt. So compared to the simulation results, in simulation results we have been found 1.9 volt, but here we have a loss 1.6 volt because of the components and the electrical and the wire. We have been used loss of wires. That's why there is a loss for the connectivity. And after that, we are trying to go to the stripboard. So these are my stripboard setups. We have been doing setups in our hardware lab. Then finally, we have found the 1.8 volt. So 1.8 volt. So it's just a low tolerance for the simulation. And so these are my comparison results between the simulations breadboard and stripboard. So here we have been used input 269 volt millivolt AC voltage. So in LTSPICE we have been found the final output is 1.9 volt, and in breadboard we have been found in 1.6 volt, and in stripboard we have been found the 1.8 volt. We are considering the stripboard output 1.8 volt, and also we have the we found the current and in a 6.33 microampere and 5.33 microampere, and here is also the 6.04 microampere. And finally, we have been found the power in calculated power using this power equation, P equals to V square by R, where it was found from this equation, P equals to IV. So this power in simulations we have been found that 12.02 microwatt, in the breadboard it's 8.53 microwatt, and in keyboard it's 10.88 microwatt. This is the final statistical table from previous researcher work and my present work. So in my case, my work is considered to the V-shape cantilever beam. So as I mentioned in my literature survey, that other researchers that they were not working on the V-shape cantilever beam, but in my case, I am working on the V-shape cantilever beam, and I have got the good output here in the for my application, and also the voltage from the mechanical beams, and also the electrical output circuit in 1.8 volt, and also found the calculated power is 10.88 microwatt, and it is a desired output for the modern pacemaker. So, and finally, that we have designed the V-shape cantilever beam energy harvester for converting mechanical vibration energy to electrical energy, and using the COMSOL software. On that terms, we have been considered the beam as a length 95 millimeter, and width is 7.5 millimeter, and thickness is 0.3 millimeter. And also we have found the optimum resonance frequency is 14.37 hertz with the voltage of 269 millivolt AC. After that, we found that the voltage in LTSPICE software simulation, we have been found that the final voltage is 1.9 volt. Finally, we are doing the breadboard and stripboard. Where breadboard we have found 1.6 volt, and in stripboard we have found 1.8 volt. Finally, we have been calculated the power, and the power is 10.88 microwatt, which is more than enough for the modern pacemaker devices. In my master's thesis, I have done this publication, and already this third paper is also ready and for submission, and also one conference paper. That is my references. Thank
Yeah, thank you. Thank you, Mr. Joy, for your nice presentation. Yep.
you.
So now time for Q&A session. And first, I would like to invite our external examiner.